Macdonald, maintainer of the set-based library. I've recently been working on the garbage collection. First page here, history of garbage collection in Objective-C. This really started with the Bone Conservative Garbage Collector, written in 1988, so it's a venerable piece of software. Lib Foundation, which was written around the same time as GNU set-base, introduced garbage collection to an Objective-C Foundation library in 1998, and I added it to GNU set-base in 1999. So Apple Cocoa introduced it in 2007. Right. Why do we have garbage collection? Well, the original reason we added it was to make things easier for a programmer. Managing memory is just a pain. So you can decrease the memory management overheads with garbage collection. You don't have to do reference counting, that kind of thing. Though we do have a good reference counting mechanism. We wanted our garbage collection system to be portable, cross-platform, because GNU is a very cross-platform development system. We wanted a single code base originally for both garbage collecting code and a non-garbage collecting version. And originally we wanted Lib Foundation compatibility because we believe in conforming to the standards, and the only other implementation that used garbage collection at all was Lib Foundation. Another reason for garbage collection was performance. Contrary to a lot of ideas, the garbage collection at the time actually seemed to work faster in real life than reference counting. That's mainly anecdotal evidence from Lib Foundation. Certainly, Lib Foundation showed that garbage collecting systems could be comparably fast to normal reference counting implementations.
I'm sorry, but isn't it that the systems which run receive faster only when they deal with a small number of objects? If you deal with a lot of objects, it's much slower. When you deal with C++, you can just block allocation on your own, you can write your own memory management, you can be a lot quicker. Anyway.
No, that's not necessarily true. I think the Bone library, for instance, does thread local garbage collection, which lets you localize where you're collecting data from, so you don't have to worry about scanning the whole of the memory, for instance. The Apple implementation also has a different mechanism for avoiding scanning all the memory all the time. And pragmatically, the code that you tend to write in something like C++ or C to handle the memory management is generally slower. Yes, you can optimize it to be faster, but you can also do that in the garbage collecting environment in Objective-C. So what you're talking about overall performance for the average user, garbage collection can work out faster. Yeah, generally. And when you're talking about customizing specific, micromanaging little tasks, you can hard code it yourself in whichever language you like. So why did we use the Bone library? Well, it was public domain code, which is kind of important. It was already very mature and stable by the time we introduced it. It was 10 years old at that point. It was quite portable. There were a lot of systems supported by the Bone library, and it was very fully featured. It did really pretty much everything you want for the garbage collector by that time. Because of its use in Lib Foundation, it had already been integrated into the GNU runtime. It's currently included in the GCC repositories, part of GCC, or at least a particular version of it is, the very latest. And it was said to perform very well. Okay, the way garbage collection is used in GNU set-base is that all the object allocation is typed collectible memory. What we mean by that is that at the point when the object is created, we know which instance variables of the object are pointers to things that we might want to keep a reference to within the garbage collection system, and we know that other parts of the instance variables are not. So the garbage collector knows about those and doesn't have to scan them. When we allocated memory generally, everything was allocated as scan collectible by default. So every bit of memory allocated could contain pointers to things, apart from the typed collectible objects. And also with the exception of GS atomic malloc zone. In the OpenStep API, you allocate memory in different zones. So we introduced that zone to say, here's a zone where you don't need to scan it. There will be no pointers in this area. The plus point of doing all that was that it was very easy to convert applications. You don't unexpectedly collect memory because all the stuff that you used to implicitly allocate on the heap in the default zone is now scanned, so it's safe in that respect, but it does mean that it's a bit slower. So more memory than necessary is scanned, and data that doesn't contain pointers would be scanned, and possibly you'd think you had a pointer and keep something allocated, essentially leak memory a little. So the use of the atomic malloc zone internally meant that actually within the base library we didn't have any of those problems. The way the root object, NS object, was changed was to ignore the allocation zone. Of course, we don't want to allocate in a particular zone anymore, we're using garbage collected memory. Auto-release, dealloc, release, retain, they're not used anymore, so they just do nothing. The retain count returns uint max, just to say this is retained as many times as possible if not going to be deallocated. I already said that. Allocated objects using the type memory, only the pointer instance variables are scanned. So, because we changed that to remove, or comment out effectively, the dealloc method, the paradigm of doing cleanup in the allocation of objects no longer works, of course. And that means that the ideal way to handle that in most objects is to invalidate the object and do explicit cleanup of things like closing file descriptors. If we can't do explicit cleanup because we don't know where we're getting rid of an object, it's hanging around somewhere, we need to use a finalization. For finalization, we added a new protocol, the GC finalize protocol. Basically, any class which conformed to that protocol was finalized. It was finalized by using the GC finalize method. The idea of that is that you shouldn't ever call that code in your own code. It's like dealloc, except that it's called by the garbage collector. So there should never be any need for you to call it, except of course you need to call the superclass implementation if you're writing a subclass of another class that's already finalized. The method's called automatically when the object is deallocated. Finalization is fairly expensive to use, so you should use it as little as possible. The problem is that when you do a garbage collection run, you finalize all the methods that have a finalizer set, and that means that you can end up executing quite a lot of code at one time. So you make the finalization method lightweight and minimize that. Weak pointers were added. A weak pointer doesn't prevent the collection of the object you're pointing to. It could be created by registering in the initialize method of the class. So whenever a class instance is created, the initialize method, or the first time a method is sent to a class, the initialize method is implicitly run. And that allows you to say all objects of that class will be finalized, will have weak pointers in future. Weak pointers in the Boehm library are not automatically zeroed. So you can get a situation where you're pointing to something, that object, because it's a weak pointer, gets collected, so your pointer is ending up pointing to nowhere. So if that's going to be a problem, the object that it's going to be deallocated needs to have a finalizer method to remove or clear that weak pointer in the other object. That's very much the same sort of situation that you get with the standard OpenStep library, where you have, say, a notification observer, and that observer gets deallocated, its dealloc method removes the object from the notification system. Control of the collector. Of course, there are times when you don't want garbage collection to happen, if you've got timing critical code, so you can temporarily disable, re-enable the collector. There are times when you think you've gone round the loop allocating lots of objects that you don't need anymore, and you want to reduce the memory footprint of your application, so you want to request a collection, either using inbuilt thresholds, so if so much memory has been allocated, then we'll do a collection, or unconditionally, we want to collect any garbage right away, no matter what. We also need to be able to register and unregister zero memory pointers. Well, that's done via native calls to the collector. The other thing we added way back then was a whole load of macros. Calls retain if you're running compiling in conventional system, and does nothing, comments it out effectively if you're compiling for a garbage collection. Similarly with all the others. The idea of that was for performance. Yes. Why use? Okay, back then, the overheads of actually making those reference counting method calls were significant. That's really not the case on the modern processor. The other reasons for putting these macros in was for reliability. Destroy is a convenient way of zeroing the pointer so that you know that the object it points to can be collected, rather than having to remember to deallocate it and then zero the pointer. You use a macro for it. Assign helps prevent mistakes in the same sort of way. It builds in a bit of intelligent standard usage, good practice. Right, the downside of that is that if you've compiled code with those macros, then if you compiled it in a garbage collecting environment, your calls to retain, release, auto-release, whatever, don't exist anymore. So your binary can't be run without a garbage collecting version of the library. I'm not sure that that's really a problem. The other downside is purely that they're a bit inelegant. So maybe we'll get rid of those macros. So, why did we want to change it all? Which is what it's really about. Well, originally we were Loop Foundation compatible. There's been no interest in garbage collection in Objective-C for many years. I know that because I know of some bugs in the code that have been there for years and no one has complained about them. So, possibly that's because the retain and release mechanism reference counting actually is good, works very well in general. But now Apple, Cocoa have introduced garbage collecting themselves and revived the interest in it. And lib foundation is obsolete, no one really uses it anymore, so there's no point in us trying to be compatible with the lib foundation implementation. So we've changed the whole focus to be Apple compatible now. We're not throwing away the existing work, really. We're keeping the Bowen library. Right, why doesn't Cocoa use it if it's so great? Well, maybe they just like their own code. Certainly they have no need for portability. Yeah, they can write code optimized for their own system. Their implementation does depend on compiler support, which they've built in, and they can do that because they have a dedicated compiler for their own system. They say they wanted more predictability and they wanted better performance. I don't actually know of any evidence that they have that, but maybe they have. Okay, what difference does using Bowen make over Apple's implementation? Well, the Apple implementation uses zeroing weak memory throughout, and Bowen doesn't have that. It does have zeroing weak pointers. Their implementation does generational garbage collection. The compiler puts stuff in the code so they can keep track of which objects have been allocated recently, and so they can look at those recent objects first when they're doing a garbage collection run, which hopefully means that they get rid of objects that they're likely not to need very quickly without having to do a full run. On the other hand, the Bowen library has thread local garbage collection, which means that you don't have to worry about stopping all threads to do a garbage collect. So there are performance differences either way. Okay, so the change to the way the base library garbage collection works to make it compatible with Objective-C, with Cocoa. Okay, all that object allocation is typed selectable. That's not a change. Stays the same. But, we have a new function, NSAllocate collectible. That's Apple API, and that will give you scanned or unscanned memory, and it will say whether that memory itself can be collected or not. Default malloc zone is unscanned, uncollectible, so you have to treat it explicitly. That's completely the opposite of the way the base library used to do it, where we had scan collectible by default. So that's a major shift in that one point. Finalization. Well, they still have finalization, but of course that is different. So now they have a finalized method where we had a GC finalized, so we have to change all our method names, but that's pretty trivial. All you need to do is implement that method in your subclass to have that class finalized. Whereas we had protocol to flag whether or not the class needs finalization. That was also easy to change. It looks cleaner and simpler. I prefer finalize as a method name for finalization. So we've already changed to implement that. Zero and weak pointers, that's a fairly big issue of difference. Cocoa added the weak keyword, underscore weak keyword, in the compiler to mark an instance variable as a zeroing weak pointer. Because we don't have the compiler support yet, though it's possible we could add it to GCC, we have a runtime mechanism to do the same sort of thing. So we've added the function gs_make weak pointer, and what you need to do is call that in the initialize method of your class to say that a particular instance variable is a weak pointer. We also have gs_assign zeroing weak pointer, which lets you assign a value to a zeroing weak pointer. Apple don't need that because their compiler implicitly does it. It knows that the pointer is a zeroing weak pointer because of the new keyword, and the compiler will do the overheads of telling the garbage collecting library that you've made an assignment to that pointer. We have to do it explicitly. Again, if someone adds compiler support, we can avoid doing that. Hopefully that's not too difficult. Notifications. That's a big part of the way OpenStep applications work, sending notifications to different objects. If a notification center retains an observer, then the observer is never going to be deallocated. Obviously, we don't want that. So we don't retain the observer, and we use a weak pointer. But if the observer is deallocated, and we haven't removed it from the notification center, we're going to get a crash when the center tries to send a notification to that object. So the observer has to be removed again somehow. Traditionally, that's done in the observer's dealloc method. But now we have a zeroing weak pointer used in the notification center. So the observers no longer need to remove themselves. We have a similar situation with key value observing, where an observer normally unregisters itself from observing an object at the point when it's deallocated. Again, we use zeroing weak pointers so we avoid the observer having to do that. It's a mechanism that's generally applicable for any sort of system where you have one object observing another object, and it avoids the need to finalize those observers. As I've said before, minimizing the use of finalization is a good thing. The other advantage is that the burden of management is lifted from the application programmer. They no longer need to worry about removing themselves as observers. They can just forget about the whole thing. Traditionally, delegates of objects are not retained. Now, that's so that you don't get retain loops causing delegates to never be released, which is the problem with a reference counting system. With a garbage collecting system, you don't have to worry about the retain loops because the garbage collector will resolve that. So we actually have no need to use weak pointers for delegates. So the fact that our zeroing weak pointers are currently different from the Apple ones is actually nothing like as big a problem as it might seem, because almost everywhere that you used to use weak pointers, or would expect to use weak pointers, you don't actually need to anymore. So, how's collection controlled? Well, before it was done directly by calls to the Boehm library. Now we use Apple's API, a new NS garbage collector class. So this class is implemented already, and you don't have to know anything about the Boehm API anymore. The default collector method of the class returns nil if garbage collection is not in use. So it's a great runtime check to see if the application is working in a garbage collecting environment. So at the moment, for instance, we use that in the regression testing suite to control which regression tests we do, depending on whether we're running with garbage collection or not. Obviously, some tests are inappropriate in different setups. Collective needed, that triggers a garbage collection. It's really the same as the functionality we had with the Boehm library, so we just wrap the Boehm library's call. There's a threshold amount of memory. If we've allocated that much memory since the last garbage collection, then a collection takes place. Collected exhaustively, we have a full garbage collection done. Disabled, enable, is enabled. They tell you whether garbage collection is in use at the moment. Okay, the NS auto release pool class. It's pretty much obsolete. adding an object to a pool obviously does nothing, there's no point doing it. Apple added the drain method, so we implemented it too. It does the same thing as collective needed, so I have no idea why Apple added that method. As far as I can see, the FAS really ought to be completely obsolete in a garbage collecting environment, but we did that for compatibility. The NS pointer array class. It's a new class introduced by Apple in macOS 10.5. Can hold pointers and or integers. It can contain nil objects and null pointers, which is a kind of departure from all the collection classes traditionally in the OpenStep API. You can tell it to use zeroing weak memory, so that items become nil or null when they're collected. So internally we implement that as using the zeroing weak pointers that the Boehm collector uses. So from the point of view of an application programmer, there's no difference there. It works exactly like the Apple implementation. Not completely implemented in GNU-Step yet. I expect that to be finished in about 2 weeks. NS hash table. When we originally implemented garbage collection in GNU-Step base way back, we added support for weak pointers there, but they were not zeroing weak pointers. Apple have taken a very different approach. They've actually removed the NS hash table object as it was and made it into a full class with support for zeroing weak pointers. So it automates the removal of collected items. We are going to change it to match that, and I imagine that will probably be ready in about 2 weeks as well. It's really the same, pretty much the same set of code as the NS pointer array. NS map table. The situation is very similar. Originally we supported weak pointers, but only for weak pointers for keys and values. So if your map is set up for weak pointers, then it was both weak pointers to the keys and weak pointers to the values. Apple have made it into a class, and they've added separate support for weak pointers for keys and weak pointers for values. We're going to make the same change. Again, you're looking about 2 weeks before that's done. So we have almost the same garbage collection functionality as Apple do. Hash table and NS map table need updating to be Nexus classes. Direct use of zeroing weak pointers remains different. That's the only difference you see between the two APIs now. That will probably change if and when someone puts in the compiler support in GCC to automate it for us. But until then, as I say, it's minimally used, so not a big deal for portability. And that's it. So essentially, an overview of all the change. Basically, we've implemented, or will have implemented within a few weeks, the entire garbage collecting API of macOS 10.5. Questions?
Excuse me, could you make it clear what's the main strategy to run garbage collector? Is it tracing from roots to objects, or reference counting, or something combined?
The Boehm, well, you really ought to look at the Boehm garbage collecting library documentation for that. Essentially, it's a conservative garbage collector. It scans memory.
Full scan from roots.
Sorry?
Okay.
A full scan?
Mm-hmm. No.
It scans everything on the stack, everything in the registers, and everything on the heap that it's been told to scan.
So it scans through all heap, which is quite expensive.
Yeah, but it will do that on separate threads. Separate heaps for separate threads, if you like. And generally speaking, it's not that expensive, because most of the memory you allocate doesn't get scanned because it knows not to scan it, because it knows there are no pointers in it, or it knows that certain sections of memory have mixtures of pointers and non-pointer parts of memory. That's called typed memory. It knows what type of memory is at different locations. So it knows which parts it needs to scan and which parts it doesn't. So it's nothing like having to scan the whole heap. And in fact, it can make good guesses about what's a valid pointer and all that kind of thing. It's really very good at minimizing that. So it's a key feature. So that's something that FOSDEM worked on for many years.
Thank you.
So how does the new GC see in the stack which are pointers and which are not? Which ones are pointers?
The stack, it doesn't know the type. It has to assume that, well, I mean, obviously it knows that some things are the frame pointers within the stack. It has an understanding of the actual stack layout. But when it comes to the actual data variables on the stack, it won't know the type. So it has some fairly basic heuristics. I mean, if it's if what it sees on the stack is an integer that has the lowest bit set, it knows it's not a pointer to a block of memory, so it won't bother looking at that. But essentially, it's going to look at the whole of the whole of the stack.
So it's still conservative on the stack.
Yeah. Anything else? Okay.